Hello guys, welcome to our channel Shubda Group of Education CC. You're watching Satish Sir's physics videos for Karnataka CET and NEET. Okay, so here to start our discussion on semiconductor electronics, an important topic. So you can expect around 4 to 5 questions from this chapter. Okay, so the density of an electron hole pair in a pure germanium is 3 into 10 to the power of minus 3. Okay, uh, 3 into 10 to the power of 16 per meter cube or per cubic meter at room temperature. On doping with aluminium, the whole density increases to what? 4.5 into 10 to the power of 22 per cubic meter. So now the electron density, okay, so doped germanium will be correct. So this particular problem is based on mass actions law. Okay, mass action law, you have already studied about it. So when number of electrons is equal to number of holes, then we can say that the number of intrinsic carrier concentration, that is what Ni is equal to N E into NH, so that it will become square, Ni square equal to Ne into NH. So now they have given that electron hole pair, in the sense it is nothing but what? Intrinsic concentration. At that time we can take Ni as 3. Okay, Ni is equal to 3 into 10 to the power of 16 per meter cube. Okay, per meter cube, as well as number of hole density, in the sense nh is going to be how much? 4.5 into 10 to the power of 22 per cubic meter. So therefore what can I say is, therefore 3 into 10 to the power of 16 to the power of 3 square, that must be equal to ne into nh is how much? 4.5 into 10 to the power of 22 here. Okay, so 3 square is how much? It is 9, right? 9 into 10 to the power of 32 divided by how much? 4.5 into 10 to the power of 22, that is equal to ne. So it implies ne is equal to how much? 2 into 10 to the power of 10. This is what? 2 into 10 to the power of 10 per cubic meter. That is the right answer for that. So the electron density must be 2 into 10 to the power of 10. Okay. The next one, a semiconductor is known to have an electron concentration of 8 into 10 to the power of 14 per cubic centimeter, and the whole concentration is 5 into 10 to the power of 12 per cubic centimeter. Okay, so the semiconductor is now. So clearly you know that number of electrons are greater than number of holes. At that time we can say that the particular semiconductor is which one? So here number of electrons are in the sense electrons are majority charge carriers, right? They are majority charge. So that's the reason why that is n type. Suppose Ne is less than NH, at that time this is the category of the semiconductor must be p type, correct? So that's the reason why, so that we can say that, so here the electron concentration is this much, 8 into 10 to the power of 14, and it is what? 5 into 10 to the power of 12 here, correct? It's a 12 one. The okay, so surge and intensity is 12, so that's the reason why we can say that number of electrons are greater than what? Number of the holes. So that's the reason why we can say that it is the n type semiconductors. Directly we can say. Okay, so that depends on the concentration of electrons as well as holes there. Okay, look at the next problem. How does the number of free electrons vary in semiconductor with temperature? Correct. So you know that the number of electrons which pass from valence band to conduction band, n is equal to a t to the power of 3 by 2 into e to the power of minus eg divided by 3 kt. Eg divided by 3 kt, right? So this is what the formula you have discussed here. So by using this one, okay, so by using this particular concept we can say that directly what you can conclude here. So directly we can, so this is Eg minus 2 kt. Okay, this is Eg minus Eg divided by 2 kt. So n is directly proportional to what? T to the power of 3 by 2. Okay, so that's the reason why temperature to the power 3 by 2 is the right answer, option B. Okay, look at the next problem here. A pure silicon at 500 Kelvin has equal number of electron and hole concentration of 1.5 into 10 to the power of 16 per cubic meter. Okay, doping by indium increases NH to 4.5 into 10 to the power of 22 per cubic meter. The doped semiconductor is off. Okay, so again I have to use the mass action law. Ni square is equal to Ne into Nh here. Okay, Ne into Nh. So let me substitute the value of Ni as 1.5 into 10 to the power of 16 to the power of 2, that is equal to Ne into, so now Nh is going to be how much? 4.5 into 10 to the power of 22. Okay, so therefore Ne is equal to how much? Ne is equal to 0.5 into 10 to the power of how much? 10 to the power of 10 here, or else it is 5 into 10 to the power of 9. Okay, 5 into 10 to the power of 9. So therefore they have given that NH is equal to what? 4.5 into 10 to the power of 22 is given. So therefore clearly I can say that NH is greater than what? Ne. So that's the reason why it is a p-type semiconductor. This must be the p-type semiconductor with Ne is equal to 5 into 10 to the power of 9. So that's the reason why option B is the right answer for this question. Okay, so look at the next problem here. The Fermi energy is the conceptually based problem. So this is you have already studied about the semiconductors, right? So the Fermi energy as well as Fermi level you have already studied about it. So Fermi energy is the maximum energy of the electrons in the matter at 0 degree Kelvin. Okay, 0 Kelvin. Okay, so that's the reason why option C is the right answer. The maximum energy occupied by the electrons at 0 Kelvin in a particular matter, that is what we call it as Fermi energy. Okay, look at the next problem. In a p-type semiconductor, the acceptor level is 57 milli electron volt above the valence band. Okay, so the maximum wavelength of the light required to produce a hole will be, okay, so hole electron pair usually. Okay, for this one I have to use E is equal to Hc divided by lambda, because they have given the energy E, as well as this is what the energy. Okay, acceptor level in the sense this must be the energy. Electron volt is the unit of what? Energy, right? So that's the reason why E is equal to Hc by lambda. So we need to calculate the value of wavelength, that is what lambda. Hc is 12400 angstrom electron volt. Okay, so divided by lambda. So this is the shortcut you have to remember here. Hc, instead of substituting the Planck's constant as well as speed of light, you can directly take the value. This is the nearest value, that is what 12,400 angstrom electron volt. So therefore let me substitute now. The value for E is 57 milli 10 to the power of minus 3 electron volt, that is equal to 12400 angstrom electron volt divided by lambda. So therefore lambda is equal to 12400 angstrom electron volt divided by 57 into 10 to the power of minus 3 electron volt. Electron volt. So 57 divided by, so this will lead you to get the answer as 217100. This is the nearest answer. So this is an option B is the right answer for this question. Okay, so thank you very much for watching this video. I will upload few more videos on semiconductor devices as well as logic gates. Please do watch them. Okay, please do share this one with your friends and colleagues to support us. Please do subscribe to our channel. If you have any doubts, make a comment on the comment box so that I can help you with. Wish you all the best for your examinations. Good luck.